finish the definition of local quantum field theory. So, having this example in mind, let's continue the definition. So we fix the space-time category. So objects will be d-1 dimensional manifolds with some structure, possibly morphisms are d-dimensional manifolds with possibly some structure. And actually, as you can see from this example, it doesn't have to be, they don't have to be manifolds. You can as well work with, say, cell complexes. And, the example here, so stat mechanics on graphs. This is the case when d equals 1 and when MD are one-dimensional cell complexes. But you can as well consider d-dimensional cell complexes and some kind of discrete models of statistical mechanics. And this will be examples of local quantum field theory as well. If the Boltzmann weights will be local, again given by products over vertices, edges, elementary cells. So we fix space-time category, and then local QT, it's the assignment when to each d-1 dimensional manifold you assign the vector space, and to a d-dimensional manifold you assign the d-dimensional vector space. A vector in the vector space corresponding to the boundary of M. So these are the data, and then the axioms. So basically what we want to do is we want to have the same properties. And the reason for this is because we want to have a local quantum field theory. So we have seen that the locality of weights, the locality of these weights implies these properties. So now we don't want to define the theory in terms of weights, but we still want it to be local, so that you can chop it up into small, so you can chop up the space-time into small pieces, and then you can glue the partition functions from the partition functions for elementary pieces. And so here are the axioms. First, well, let me switch first and second one to an empty space. And just because it's not statistical mechanics, so we'll complexify the spaces. So this is a C. Second, if we have two d-1 dimensional manifolds which are disjoint, the vector space assigned to these manifolds is the tensor product. Third, just as over here, when we have two d-dimensional manifolds with disjoint d-dimensional manifolds, the vector which we assign to the disjoint union is the tensor product of vectors, and it's a vector in the tensor product of spaces corresponding to the boundaries of components. Four, just as over here, and have it like this, I should say that, and I mentioned it before, that we will consider when the theories where the spacetimes are oriented. So in this case, there should be pairing between n and n with the opposite orientation, and this pairing should be Hermitian. And 5. For this I have to raise some of it. Just as in the example with the graphs, if we have a spacetime whose boundary consists of 3 pieces, M1, M2, and if we have an isomorphism in the appropriate category between these two components of the boundary, it should be orientation reversing. Because, say, for a graph, we want to glue the edges of the opposite orientation. So in this case, it leads to I forgot 4 prime. If we have an isomorphism, say orientation preserving isomorphism, then it leads to a linear map vector spaces. And if it's orientation reserving, well, it still leads to okay, that's it. So if it's orientation preserving, then it's a linear isomorphism. It's a C-linear isomorphism. And if, I'll continue here, if F is orientation reversing, then S of F is C antilinear.
Isn't it just a map to the dual space?
Well, it's
if
a
we have the
division
pairing,
pairing, so it's the question whether, so you know, the map is C antilinear if it's not C linear, but if it conjugates when you multiply by complex scalars.
Is there a subtle reason why we don't use the word functor in this business right now? I mean, because it's just, well, it seems like a functor that preserves some duality and monadal structure. And
yes.
Right. But the only difference is that this self-gluing is not really captured by the functoriality, right?
It's the functoriality, exactly. It's, I mean, I don't use I should have used the word factor, but I want to keep it, it's slightly more general situation when it's probably something like an operand or something like this. When you see,
well, functor, you have source and target.
Yeah.
Here we have manifold with several boundaries. Each of them can be considered as a source.
Right. But
Each of them is target.
but the only problem is the self-gluing, right? I mean, the only. Oh, right. I see what you mean. So we can also ignore some of the parts of the boundary as well. I mean.
Right. Yeah.
Well, but with the duality, we can always flip a target boundary to a source boundary.
Source, but you can in this case you can take a part of source and put it to the target.
So the only thing is self-gluing, which is that's not contained in.
That's
in the functor.
not contained. Yeah.
But I mean, the duality fixes. We can shift from.
it can be contained. I mean, actually, if you say that it's a monoidal functor, then it is contained. So you're right. I should have said. Essentially, these axioms, so the bottom line of these axioms is that we have a monoidal functor from space-time to vector spaces. So, I mean, if these vectors are finite dimensional, then that's what it is. But realistically speaking, all these spaces will be infinite dimensional. So let's just.
But when concretely speaking, when we actually have something constructed mathematically.
Yes, then it's well, but then it's more complicated. Then.
Well, never mind.
Yeah. Yeah. In this beautiful case of topological quantum field theory, which is the Chern-Simons, one can actually construct finite dimensional quantum field theory combinatorially. But that's exactly what I don't want to talk about. We were talking about it for 2 years almost, sort of, on various occasions. So let's talk about something else now. So it's something else is not as well defined, but so it's even more interesting maybe to make it better defined. So okay, so this leads to anti-linear map between these spaces, and we have the permission pairing. So the axiom is that if you apply just as over here, identity, permission pairing, then identity S of F identity to Z M, we will have Z M F in the vector space D M prime, where MF is M with these components of the boundary the identified by F. So that's the result of the gluing. Just the picture is more or less the same, except now it's a manifold with 3 components of the boundary.
When you say local QFT, what does the word local signify?
It signifies this axiom. I mean, it signifies that, say, you can cut the manifold in several pieces, and then having these factorization properties and this pairing, you can glue the partition function for the bigger manifold from the pieces.
So the global situation is determined by the local.
Exactly.
So it's like a sheaf condition.
Exactly. And then you can continue it infinitely many times, and so you can glue the whole thing from infinitesimally small pieces. That's the idea. Okay, so this is the framework. And you see that it's rooted in these very simple combinatorial models in statistical mechanics. And so somehow it existed in statistical mechanics, but it never made it further than this combinatorial setting before this kind of ideas, before these papers by Atiyah and Siegel. So Atiyah suggested this framework for topological quantum field theories, and Siegel suggested it for conformal field theories. And so I think Siegel actually never published this preprint versions of his notes, and then somehow I think he was forced to publish it in one of in a volume that was published on the occasion of his 60th birthday. So it's just this collection of informal notes that existed because they were just published, and so Actually, it has some very nice ideas. So it's how this setting can be implemented for conformal field theories. Okay, so now let's look at how to implement this setting. If you want to say, the question is what to do if we have a classical field theory, and given this classical field theory, we want to construct something like this. So here's a very naive idea. So suppose that field theory how to construct local QFT in this sense. Well, let's take scalar Bose field as an example. So here is the very naive proposition. Let's take the space, this vector space, D minus one dimensional, to be the space of functionals on maps phi, we call it B, from n D minus 1 to R. Just a set, not a whole G. And let's say, let's take smooth maps. And then let's define the vector Z M. Now it's a functional on this mass. I will define it like this. The integral of e to the I s of phi over h, integral over all classical fields, such that if you restrict this field on the boundary, it is equal to V. And here Sm is the action that we discussed already. So it's integral over m, 1/2, dphi minus dphi dx. The assumption is that m is Riemannian. And phi is a map, smooth map from M to R. So let's suppose that everything is well defined. I mean, well defined is a bad word. Let's suppose that everything is defined. So then, when we have a situation like this, when we have three pieces of boundary for M, we have dm1, dm2, we have the identification of them by F. So then we just take Z M. It depends on fields on maps from here to R, maps from this component, so B prime are maps from M prime to R, B1 and 1 to R, B2 and 2 to R, B2. We identify the these maps in the sense that we take V1 to be the pullback of V2, and then we integrate with respect to V2, and we will get the using the forbidden theorem when you can replace the integration order, so we will get this. So, and of course, what is written here is some kind of naive continuous analog of what we had for graphs. For graphs, the states, instead of a manifold, we had a graph, and instead of classical field, we had these states on edges. So in some sense, integration over d phi is the analog of the summation over inner states. And these weights, well, these are the analogs of WC. And this is the analog of sigma out. So, and I should say at this point that there are two types of quantum field theories. So, one type, so I don't know what's happening. There is no standard. Let's call them unitary quantum field theory. This is when you take e to the I over h and then the action function. And the second type is Euclidean, where it's more like statistical mechanics, where it's e to the minus s and p over t. And in this setting, s is more like the energy of the state. And this is more like the Boltzmann weight. So in some sense, this setting is really parallel to the statistical mechanical model that I was describing for graphs. So then this would be really the analog of W sigma. So, well, so this is the program. But, of course, I'm grateful for the patience here, so nobody started to shout that it doesn't make sense. And it doesn't make sense. And so that's the whole problem in quantum field theory, that there is this great proposal which doesn't make sense. So somehow and it's clear that from this finite dimensional analog that maybe there is a way to make it meaningful. So, what are the possibilities? So, possibility number one, it's the most natural one. Let's approximate M by a cell complex. And just not only M, but the whole space-time category, let's approximate it by metrized cell complexes. So then the space of fields will be the space of maps. Well, then these scalar fields, they'll be basically maps from vertices of the cell complex to R. Phi will be mapped from vertices to R. And you can imagine some kind of discrete approximation to this functional where you replace these differentials by kind of discrete versions of derivatives, simply by differences of the fields at the neighboring vertices. So then the integral becomes finite dimensional. The space HDM becomes L2 on R to the number of vertices on the boundary. And it's a finite dimensional model in the sense that it's still not finite sets as we had for graphs, but it's a collection of finite dimensional integrals where you can actually at least talk about convergence, and then we can ask some reasonable questions about convergence, and if these integrals converge, either absolutely or conditionally. In this case, there is no chance that they will be convergent absolutely, but they may converge conditionally. So at least these functions will be defined. But then, problem 1 is how to prove that there exists continuous limit. And problem 2, that prove that it doesn't depend on the approximation. And these are extremely hard problems, and this is what constructive field theory project is. So people who work in constructive field theory, it's mostly analysis, analytical problems, and the analytical problems are to prove the convergence, to prove the existence of these limits. And these are extremely hard. So, because they are so hard, one can try to make a shortcut. And basically, if somebody wants to avoid analysis, so one should think about some ways how to replace the analysis by some kind of algebra. And maybe geometry is necessary. So, so usually analytical problems are more complicated than algebraic problems. And, so if we can somehow avoid analysis, then maybe we have a chance to say something about the theory. So then we have this semi-classical proposal, which is based on the following. So you see there is a parameter here, h. So this whole theory depends on a real parameter h. And then the idea is that maybe we can construct some kind of asymptotical expansion as h goes to 0, and just to work with this asymptotical expansion within the framework of local quantum field theory. So that this partition function now will be formal power series in h, and so on. So let me make a certain outline, and then we'll follow this outline. So you can see that this is some sort of non-existing oscillating integral. And if there is a gauge symmetry, then it's even worse. Then there is an infinite dimensional group that, with respect to which this integrand is invariant. So we know that this integral is proportional to the volume of this group. So as a first step, we have to get rid of this volume. In other words, to pass to the quotient, the space of fields modulo the gauge group. And so we will discuss this. But even if there is no gauge action, so if we have some kind of finite dimensional, this is finite dimensional compact manifold, we have some function f of x over h. Let's assume that we have some volume form. The question is how to find the asymptotical expansion of such integral as h goes to 0. And so this will be our first task, to find this asymptotical expansion, assuming that f has finitely many critical points. Okay, so second, well, that's a semi-classical proposal. So second, we will use this answer to construct Z. So, well, jumping ahead, many of you knows this, that this asymptotical expansion is given by the contributions from critical points of the function. It's the sum of the critical points, and then there are these oscillating terms, and then the formal power series in H. So, we'll use this answer in order to construct the ansatz for this partition function, and then, of course, the task will be to check whether this ansatz satisfies the gluing axioms. So, if it does, then we constructed a formal version of quantum field theory. And then we shouldn't worry about the integrals, because all we will have to deal with, all we will have to do is to work with these asymptotical expansions. And to work with asymptotical expansions is essentially null. There's practically no analysis involved there. So, I mean, there will be an analysis involved there, but it's minuscule comparing to this task. So this is one proposal. And this is what we will discuss. That's sort of for the rest of the class. And there is one special case where we can actually construct local quantum field theory without this idea. And that's the quantum mechanics. So, in this case, we can get by without path integral. So in this case, we can use the Schrödinger equation. To construct Z m in H. And we can compare first. And second, we can compare this construction from the Schrödinger equation, which is mathematically completely meaningful. We can compare it with the semi-classical path integral. And remarkably, the answers coincide. They are written in completely different terms. So, from the Schrödinger equation, the asymptotical expansion as h goes to 0 is just the asymptotical analysis of certain PDE equations, partial differential equations. In this way, we will have the partition function as the series in H, with each coefficient being given by the sum of Feynman diagrams. But remarkably enough, these two answers coincide. And so this is a good sign which indicates that maybe this proposal is not so outrageous, so maybe there is something there for dimensions greater than 1. Okay, so this is the plan. So now we should start somewhere. So we see this is somehow a zero-dimensional thing. This is one-dimensional thing. And then this is the d-dimensional thing with d greater than 1. So there is an issue in hierarchy of complexity. So let's start with the finite dimensional integral with this asymptotical analysis. Then we will compare the Schrödinger semi-classical asymptotics with the finite diagrams, and then I will argue that it's probably reasonable to construct theories in this way for any dimensions. Well, so I think there is a growing attention to the to the clock, so let's finish 5 minutes early. That's an actual break. After the break, we will start with finite dimensional integrals. So the next lecture will be at 3:15.